Okay, in this video, we're going to go over section 4.6 dealing with linear approximations and differentials. And in this section, we will use linear approximations to estimate a quantity. Then we're going to solve applications by estimating the change in a given variable. And then we're going to write the formula for dy for a given function. Okay, so we'll begin with linear approximation and how to use those to estimate a quantity. We're going to assume that f is differentiable on an interval containing the point A. So here the slope of the line tangent to the curve at the point A comma f of A is going to be f prime of A. And that means that the equation of the tangent line will be this: y equal f of A equaling to f prime of A times the quantity x minus A. Okay. Or we can say this, which will be the same as L of x. Now, I'm going to go ahead and derive that particular formula that you see here. So let's say, and if you recall, back in college algebra, or any type of algebra that you might have taken, like intermediate algebra, when you were dealing with the point slope form of the equation of the line, it was usually this: y minus y1 is equal to the slope, that's m, times x minus x1. And in this case here, we have a point A comma f of A. And you were told that the slope, which I'm going to call m, that's going to be f prime of A. And that's actually the slope of the tangent line to the curve at point A. So if I do some substitution here in this point slope form, I'm going to have y minus y1, which is going to be, in this case, f of A, because here A is going to be x, x1, f of A is y1. So that means y1 will be f of A. So be y minus f of A equaling to the slope m, that's actually f prime of A, multiplied by x minus x1, which is A. Now, if I solve this equation for A by moving the minus f of A over to the other side, I'm going to have y equal f of A. And that'd be plus f prime of A times x minus A. So that's where this comes from. That's how that's derived, from the point slope form of a linear equation. Okay, now that's also going to represent L of x, which is going to be the new function L, called the linear approximation to f at A. Okay, and that is, if f and f prime are easy to evaluate at A, then the value of f at points near A is easily approximated using that linear approximation. So here, this is the linear approximation formula. F of x is approximately equal to L of x, equaling to f of A plus f prime of A times the quantity x minus A. Okay, so here is pretty much an illustration of that. So if we let x approach A, then your approximation is going to improve. Okay, it gets better and better when you let x approach A. And of course, this line right here in red is the tangent line, and the curve represents y equal f of x. Right, so here's our definition, pretty much summed up. F is differentiable. If we say f is differentiable on the interval I containing the point A, the linear approximation to f at A is a linear function. And that's L of X is going to be equal to F of A plus F prime of A times the quantity X minus A for X in the interval I. Okay. So we're going to be using this to solve some examples where we're going to estimate quantities. We're not going to come up with the exact values here from our calculator. We're going to be using that linear approximation equation to estimate. So on the next page, you'll want to use a linear approximation to estimate the following quantity, which is the square root of 153. Okay, so we're going to start off by letting X be whatever is underneath that square root. So here underneath it is 153. So we're going to let X equal to 153. So here we need a function for this. And in this case, since we're dealing with the square root, our function f of X will be equal to the square root of X. So f of X will be equal to the square root of X. And now part of that linear approximation function requires us to find the derivative of f of X. So I need f prime of X as well. Now, what I'm going to do is change the square root of X to its equivalent exponential form. And that would be X to the 1/2 power. And take the derivative of X to the 1/2 by bringing the power in front, copy the X over to the 1 less power, which would be X to the negative 1/2. So if I write that using positive exponents, this will be 1/2. The X goes in the denominator as a positive 1/2 power. And X to the 1/2 is the same as the square root of X. So this will be 1/2 square root of X. Okay. Now, if you want to, you might pretty much skip all these intermediate steps getting to 1/2 square root of X if you already know the derivative of the square root of X. All right, now, since I let X equal 153, what I need to do here is choose some value of A that's closest to 153 and is a perfect square. Because of course, I can take the square root of a perfect square and get a whole number from it. So I'm going to list a partial listing of perfect squares, like 9 squared is equal to 81. 10 squared is 100. I'm just trying to pick a perfect square that's closest to 153. 11 squared will be 121. 12 squared is 144. 13 squared is 169. Well, I see 153 is between 144 and 169. So I need to pick the one that's closest to it. Well, 144 is closer to 153 than 169 is to 153. So I'm going to choose A to be equal to 144. And then I'm going to evaluate f of A and f prime of A. So let's start with f of A. And I'm letting A be 144. So f of 144. And here f of X is the square root of X, by the way. So I'm going to substitute that with the square root of 144. Substitute the X with 144. So the square root of 144 is 12. So at A equaling to 144, f of X will be equal to 12. Now I need f prime of A. That's going to be f prime of A again is 144. Now f prime of X was 1/2 square root of X. So this will be 1/2 square root of x, which is 144. So this is 1 over 2 times. The square root of 144 is 12. So I got 1 over 2 times 2. So it'd be 1 over, well, 12 times 2, that'll be 24. So at a equal 144, f prime of x will be 1 over 24. Now I have enough information that I need to use a linear approximation formula, which is, of course, L of x is equal to f of a plus f prime of a times the quantity x minus a. All right, so let's do our substitution here. All right, L of x is going to be f of a. We found that out to be 12. Plus f prime of a, that was 1 over 24, times x, that's 153. We let x be 153, minus a, that's 144. I'm going to bring down L of x is equal to 12 plus 1 over 24, and then subtract 144 from 153, you'll end up with 9. And then use our calculator to get L of x. So in this case here, if I do 12 plus, and I'm going to put 1 divided by 24 in parentheses, times 9. So I come up with 12.375. Excuse me. And what that means here is this will be the approximate value of the square root of 153. So this is approximately 12.375. That's using the linear approximation approach. Now, if I did this in the calculator, this would be second x squared and then 153. You'll see how close we are to the exact value, okay? All right, but keep in mind in the homework, you're not gonna be allowed to type in the exact value. You have to go through this approach, this method, to find that or estimate that quantity. So that would be the 12.375 would be the estimate for the square root of 153. Excuse me again. All right, here's example 2. Let's say I want to use linear approximation to estimate the cube root of 23. The cube root of 23. So what I need to do here first is let x be what's underneath the radical. So I'm letting x equal to the 23. Now, the function for that, f of x, would be the cube root of x. Because I need f of x, so I need f prime of x. F of x will be the cube root of x, because that's going to be written in terms of x. And then I can find out what f prime of x is going to be. Let me write the cube root of x as x to the 1/3, and then take the derivative of x to the 1/3 power. That means I bring the exponent in front, copy the x over to the 1 less power. 1/3 minus 1 whole will be -2/3. And of course, if you didn't know that, you can do this in the calculator. You'll do 1 divided by 3 for 1/3 minus a whole. Press the math key and then select number 1 for fraction. You'll get -2/3 as your exponent. All right, but I am going to rewrite this as 1/3 times x to the +2/3. I'm just going to put the x in the denominator. and write the negative 2/3 as a positive exponent. Okay, so I have 1/3 x to the 2/3 for f prime of x. Now, since I let x equal 23, I need to choose some value of a that's closest to 23 and is a perfect cube because I'm dealing with the cube root. So let's list some perfect cubes here, like 1 cubed, that's 1. 2 cubed is 8. 3 cubed is 27. Well, 23 is between 8 and 27, but I need to pick the one that's closest to 23. Let's pick the perfect cube that's closest to 23. Well, 27 is closer to 23 than 8 is to 23. So let's use 27. So our A would be equal to 27. Now from that, we're going to evaluate what f of A is. And f of x is the cube root of x. Well, A is 27, so let's evaluate f of 27. And then substitute the x in f of x with 27. So this will be the cube root of 27. Well, the cube root of 27 is 3. So f of A at A equal 27 would be 3. Now f prime of A, f prime of A, that's going to be f prime of A again, that's 27. And in this case here, f prime of x is 1/3, x to the 2/3. So we're going to substitute the x with 27. So I'm going to have 1/3 times x, which is 27. And that's raised to the 2/3 power. I normally have a 1 in the numerator, but in the denominator, I need to do this. I need to do 3 times 27. Press the hat key for your exponent. 2/3 will be 2 divided by 3. Then I can press enter. I'm going to get 27 in this case. So at A equal 27, f prime of A will be 1/27. So now we can go ahead and use the linear approximation equation. L of x is equal to f of A plus f prime of A times x minus A. And in this case here, L of x will be equal to f of A, we found that out to be 3, plus f prime of A is 1/27, times x. In this case, we let x be 23. We let x be 23, minus A was 27. And now if I do 23 minus 27, that would be -4. So I have L of x is equal to 3 plus 1/27 times -4. So in the calculator, if I do 3 plus, let's see, 1 divided by 27 in parentheses times -4. And let's say I want to round this off to 3 decimal places. This will be 2.852. All right, so that would be the approximate value for this cube root of 23. That's approximately 2.852. All right, now if I want, now for the exact value, if I did press the math key and then select number 4 for the cube root, then type in 23, you'll see how close we are to the exact value using the linear approximation method. All right, let's look at another example. Let's say I want to use a linear approximation to estimate the natural logarithm of 1.05. The natural logarithm of 1.05. And we're going to be choosing the value of a to produce a small error. So here, let's start out by letting x equal to what's inside the parentheses, 1.05. That way I can identify what my function will be for this case here. Since I have ln of 1.05, that means f of x will be equal to ln of x. And I can find the derivative of ln of x. So f prime of x would be the derivative of ln of x, which is 1 over x. Okay. This was back in chapter 3 when we were taking derivatives of logarithmic functions. One of them is the natural log of x. Its derivative will be 1 over x. All right, since I let x equal 1.05, I want to choose some value of a that I can easily find the natural log of. And if I choose a to be equal to 1, the natural log of 1 will be equal to 0. So I'm choosing a is equal to 1. All right, so let's evaluate f of a. And a is 1, so f of 1 will be this. Just substitute the x with the 1 in f of x, so this means ln of 1. So the natural logarithm of 1 would be 0. Okay. So at a equal 1, f of a will be 0. And f prime of a, well, f prime of x is 1 over x, but here a is 1, so f prime of 1, that's going to be 1 over 1, which is 1. So from here, I can use the linear approximation formula. And that's L of x is equal to f of a plus f prime of a times x minus a. So here f of a is 0. F prime of a, that's 1, times x, which is 1.05, minus a, which is 1. Okay, so if I subtract 1 from 1.05, I would get 0.05. 0.05 times 1 is 0.05 plus 0 ends up being 0.05. So that would be the approximation of the natural log of 1.05. Now, let's say if I want to find the exact value, that way you can see how close this is. So if I do ln 1.05, close parentheses, you'll see how close that is. Using the linear approximation method, that value there is close to the exact value. All right, let's look at one more of these linear approximation problems here. All right, so in this case here, we got e to the negative 0.05, and we're going to use linear approximation to estimate that quantity. And we're going to choose the value of a to produce a small error. So here I'm going to let x be the exponent for the e, which is negative 0.05. So in this case here, f of x is going to be the function e to the x. Now, when we find f prime of x, this will be the very easy derivative to take. This is the easiest one to do. The derivative of e to the x is e to the x. Okay. Now, since I let x equal negative 0.05, let's choose a value for a that I can easily evaluate e to that power. Well, let's use 0. Since negative 0.05 is close to 0, so let's use 0 for a. And then we're going to evaluate f of a and f prime of a. Well, f of a, since a is 0, that means f of 0, e to the f of x equal e to the x, so I'll substitute the x with 0, so e to the 0 is 1. Keep in mind, any non-zero number to a 0 power is 1. And f prime of a, that would mean f prime of 0. And again, f prime of x is equal to e to the x as well. So e to the 0 is 1. Now we can use our linear approximation of L of x is equal to f of a plus f prime of a times the quantity x minus a. So here L of x is equal to f of a was 1 plus f prime of a is also 1 times x, which is negative 0.05 minus a, which is 0. All right, so L of x is equal to 1 plus negative 0.05 minus 0 is negative 0.05. And I'll go ahead and type that into the calculator. In this case here, this will be 1 plus 1 times negative 0.05. This will end up being 0.95. So this will be the approximate value for e to the negative 0.05. I'll say approximate. Now, again, if you type that in the calculator by doing second ln and negative 0.05, here we were only limited to 2 decimal places. So here you get like 0.95, 1229, 4245. Okay, so that's how we apply the linear approximation method to estimate quantities here. All right, now on the next page, you'll find a variation of linear approximation. So this is just one of those applications here. Okay, so let me zoom in just a little bit so you can see this. I apologize for using the front and the back to do my notes. Linear approximation says that a function f can be approximated as this. F of x is approximately f of a plus f prime of a times the quantity x minus a. A is fixed and x is a nearby point. Here we can rewrite this as this. If I take that f of a and move it over to where f of x is, I'm going to have f of x minus f of a, and that's approximately equal to f prime of x times the quantity x minus a. Okay. Now that f of x minus the f of a, here we're going to be using this notation called delta. That's the Greek letter delta to denote change. Here you have the change in your y values here. So that's going to be denoted by delta y. And here that x minus a, that's going to be denoted by the change in x, which is going to be delta x. So as you can see, the factor x minus a is the change in the x coordinate between a and some nearby point x. Also, f of x minus f of a is the corresponding change in the y coordinate. So because of that, this can be shortened to this. The change in y is approximately equal to f prime of x times the change in x, or delta x. And as you can see here in this illustration, you'll see what that means. Here's a and here's x. That distance from a to x, or from x to a, is the change in x, or delta x. Now, here's the black curve of y equal f of x. So if this is a, then that point would be a f of a. And if this is x, that point here will be x f of x. Now, it's going to be this distance right here. That's the change in y. F of x minus f of a. That distance there that you see with the yellow arrows represents a change in y. This distance right here represents f prime of a times delta x. That's the slope of the tangent line, which is in red, times the change in x. Okay. Now, on the next page is the relationship between delta x and delta y. So let's say that f of x is differentiable on the interval I containing the point A. The change in the value of f between 2 points A and A plus delta x is approximately this. The change in y is approximately equal to f prime of a times delta x. All right, so we're going to be using that to do a couple of examples that are related to the change in x and the change in y. Starting with example 5. Let's say I want to approximate the change in the volume of a sphere when its radius changes from r is equal to 30 feet to r is equal to 30.2 feet. And here you're given that the volume in terms of r is equal to 4/3 pi r cubed. Okay. And of course, r is the volume, r is the radius of that sphere, and v is the volume. So I'll go ahead and write down the formula. All right. Now we're going from a to a plus delta x. So this right here is a. This right here is a plus delta x. Let's find out what delta x is. And of course, a plus delta x, if you recall, that's that 30.02. And a is going to be 30, so this is 30 plus the change in x equaling to 30.02. And if I subtract 30 from 30.02, that means that the change in x is equal to 0.02. That would be the change in x. In fact, let me change those x's to r's because we're dealing with radius here. So this will be a plus delta r. This will be delta r as well. So it's delta r, and delta r, since we're dealing with radius here in this problem. All right, now I need to find out the derivative of this. And let me change that v to v of r, just so I can be consistent with what I'm doing here. So that's V of R. Now I need V prime of R. Or better yet, let me change the R to an A. So V of A is equal to 4/3 pi times A cubed. And then take that derivative. V prime of A would be equal to, now 4/3 pi is a constant, so I'm going to bring that down. The derivative of A cubed, that will be 3A squared. All right. So now if I simplify that, the 3's divide out. You'll be left with V prime of A equaling to 4 pi A squared. All right. All right, so now we're going to approximate the change in volume. So here the change in volume in this case would be equal to or approximately equal to V prime of A times delta R. V prime of A would be 4A squared. Not 4A squared, 4 pi A squared. And then times delta R. This is approximately equal to, all right, 4 pi. A is 30 feet. That's going to be squared times delta R will be 0.02. So the change in the volume, if I do this on the calculator, would be this. Let's see, 4. Now for pi will be second in the hat key for the pi. 30, and we square it times 0.02. So the 2 decimal places, this will be 226.19. And this is in cubic feet. Reason for that is volume is always in cubic units. So we have to use cubic feet for this answer. All right, so that represents the approximate change in volume of a sphere when the radius goes from 30 feet to 30.02 feet. All right. Example 6 looks like this. Let's say we want to approximate the change in the atmospheric pressure when the altitude increases from Z is equal to 6 kilometers to Z is equal to 6.04 kilometers using the formula P of Z is equal to 1000 e to the negative Z over 10. So this is what A is going to be 6. And it's going to be A plus delta R. Okay. But I can go ahead and use those Z's if I want to. Okay. I'll do that. Since Z is equal to 6, and then Z plus some change in Z is equal to 6.04. And I know C is 6, so that means 6 plus delta Z is equal to 6.04. Subtract 6. That means delta Z is equal to 0.04. That's the change in Z. Now I have P of Z is equal to 1,000 e to the negative z over t. I mean z over 10. Let's find this derivative, p prime of z. All right, that constant, we bring that down. The derivative of e to the negative z over 10 would be e to the negative z over 10. But of course, we have to apply the chain rule to find the derivative of negative z over 10, which is actually going to be a negative 1/10. Because that negative z over 10 is like negative 1/10 times z. You take its derivative, you'll end up with negative 1/10. And if I simplify this, that 10 goes into this 1,000 100 times. And then I got this negative, so p prime of z is equal to negative 100 e to the negative z over 10. So now the change in p is this, p prime of z times the change in z. I should say approximately equal to. So here delta p is approximately equal to p prime of z. We found that out to be negative 100 e to the negative z over 10 times delta z. All right, we're going to substitute the z in with 6 and the delta z with 0.04. So delta p is approximately equal to negative 100 e to the z, negative z. Well, z is 6, so this will be negative 6/10 times z. That delta z is 0.04. Delta z is 0.04. Now, for this problem, they want the exact value, not the approximate value. They want the exact expression here. So let's simplify this. 0.04 times negative 100 would be negative 4. And then that would be e to the, we're going to reduce negative 6/10 to negative 3/5. This will be the type of answer that the homework in my math lab would want. Okay, so do be aware that I'm just giving you a heads up on that for those of you who are in my class doing the homework or on my math lab. They'll want this as an exact answer. Okay. On the next page is just a summary of the uses of linear approximation. And that would be this. If you were approximating f near x equal a, then you would use the f of x is approximately equal to L of x, which is exactly equal to f of a plus f prime of a times the quantity at x minus a. That's the one that we use in the first 4 examples in this video. But to approximate the change in y in the dependent variable when x changes from a to a plus delta x, then you'll use this. The delta y is approximately equal to f prime of a times delta x, which is what we use in those previous 2 examples. Okay, last thing we'll talk about in this video would be differentials. And this is not hard. So here we're going to introduce an important concept that allows us to distinguish 2 related quantities. One of them will be the change in the function y equal f of x as x changes from a to a plus delta x, which we call delta y as before, and the change in the linear approximation y equal L of x as x changes from a to a plus delta x, which we will call the differential dy. So here's the definition of differentials. Here we're going to let f be differentiable on the interval containing x. A small change in x is denoted by the differential dx, the corresponding change in f is approximated by the differential dy equaling to f prime of x times dx. That is, if we have the change in y equaling to f of x plus dx minus f of x, that's going to be approximately dy equaling to f prime of x dx. So basically, you just have to just take the derivative of your f of x function and use this notation, dy equaling to f prime of x times dx. And by the way, if you have to take calculus 2, and if we do integration, where you have to do integration by substitution, you'll be using differentials in this case. So let's look at a few examples, like example 7. Let's consider the following function and express the relationship between a small change in x and the corresponding change in y in the form dy is equal to f prime of x dx. All right, so in this case here, we got y equal 5x plus 1. Y equal 5x plus 1. All right, so if I let f of x equal to 5x plus 1, let's find out what f prime of x is going to be. Well, that's simple. The derivative of 5x will just be 5. And the derivative of 1, which is a constant, that's going to be 0. So f prime of x will be 5. And then we'll use that form dy dx, just dy is equal to f prime of x dx. So dy, we bring that down, is equal to f prime of x, we found that out to be 5. And then bring over dx. So dy would be equal to 5 dx. Okay. Example 8, we got f of x is equal to 1 over x to the 11th. And we're going to do the same thing as we did in example 7. Express the relationship between a small change in x and the corresponding change in y in the form dy is equal to f prime of x dx. All right, let's rewrite that function f of x using negative exponents. 1 over x to the 11th will be the same as x to the negative 11. And then find out what f prime of x will be. So f prime of x is going to be equal to, here we bring the power down, that's a negative 11, copy the x over to the 1 less power. Negative 11 minus 1 will be negative 12, so it'll be negative 11 x to the negative 12. Using positive exponents, this will be negative 11 divided by x to the 12. I just bring the x in the denominator and change that exponent of negative 12 to positive 12. Okay. And then the form is dy is equal to f prime of x dx. So substitute f prime of x with negative 11 over x to the 12. Bring down the dx. That is what your differential is. Dy is equal to negative 11 over x squared times dx. Okay. Now on to the last page. Example 9. Here we got f of x equal e to the 4x, and we're going to express the relationship between a small change in x and the corresponding change in y in the form dy is equal to f prime of x dx. All right, in this case here, let's find the derivative of e to the 4x. Here we have to apply the chain rule. So f prime of x is equal to, the derivative of e to the 4x is e to the 4x times the derivative of 4x. So we have to apply that chain rule. The derivative of 4x is 4. So this will be 4e to the 4x. So now, using dy equaling to f prime of x dx, you just substitute f prime of x with 4e to the 4x. So dy then will be equal to 4e to the 4x dx. Okay. All right, example 10. Here we got f of x is equal to 6 minus a cosine of x. Okay, and we're going to write this in the form of dy equal f prime of x dx. Well, let's find out what f prime of x is going to be. All right, the derivative of 6 is 0. So I'll bring down the minus sign, minus a. The derivative of the cosine of x, if you recall from one of your derivatives of your trigonometric functions, the derivative of the cosine of x will be negative sine of x. So negative times negative is a positive, so that means I'll have f prime of x being equal to a times the sine of x. So now dy is equal to f prime of x dx. That would mean dy is equal to a sine of x dx. All right, and that's our final answer for that. Okay, example 11. We got y equal 3x cubed minus 3x. All right, and we want to write this in the form of dy equal f of x, f prime of x dx. dy equal f prime of x dx. Well, let me change y to f of x because f of x and y mean the same thing. So f of x is equal to 3x cubed minus 3x. Take the derivative of that, f prime of x would be, let's see, 9x squared minus 3. Derivative of 3x cubed is 9x squared minus the derivative of 3x is 3. And then the form that we're using is dy is equal to f prime of x dx. So dy would be equal to f prime of x, that's the 9x squared, minus 3 times dx. Notice I put 9x squared minus 3 in parentheses, because if I left that off, then that 3 will be attached to the dx. Okay, so for the whole thing, multiply by dx, I need parentheses. And finally, example 12. Here we got f of x is equal to the cotangent of 10x. And we want to express this in the form of dy is equal to f prime of x dx. Well, let's take its derivative, f prime of x. The derivative of the cotangent, if you recall from one of your 6 trigonometric functions, the derivative of the cotangent is going to be negative cosecant squared of, in this case, 10x. And then multiply that by the inside derivative. You have to apply the chain rule here. The derivative of 10x is 10. So if I simplify that, I'll put the 10 in front, so it'll be negative 10 cosecant squared 10x. Right? And in the form dy is equal to f prime of x dx, that would mean dy is equal to, well, f prime of x is going to be that negative 10 times the cosecant square of 10x times dx. Okay. All right, so that does conclude this video, section 4.6, dealing with linear approximations and differentials. Feel free to contact me if you have any questions about any of the problems that were presented in this video, or if you have any questions about the homework in my math lab.